All right, what's the connection between relations and matrices? And the answer is every relation going from X to Y can be represented by a relational matrix A. And here's how you do it. So I've got a relation going from X to Y. First, I need an ordering of X and an ordering of Y. Remember, X and Y are sets, so they don't naturally have an order. But to be able to create a relational matrix, I give them an order. So in the following example, I'm going to let R1 go from X to Y, and X is going to be the set ABC, and Y is going to be the set 1, 2. And the relation that I'm going to make up simply sends A to 1, A to 2, and B to 1. Certainly, that is a relation going from X to Y. How do I represent it by a matrix? Well, the set X, which is the domain, is going to be represented by the rows. So I have the rows. There's an A row, a B row, and a C row. The set Y, under the ordering that's natural, so 1's going to go first and 2's going to go second, are represented by the columns. All right, so this matrix is going to have 3 rows and 2 columns. And what am I going to do? Well, if the ordered pair is in my relation, then I'm going to put a 1 in the appropriate slot. If an ordered pair is not in my relation, I'm going to put a 0. So here my relation has an A1. This is the A1 slot because it's row A, column 1. So I put a 1. It also has an A2 in my relation. So in that position, row A, column 2, I'm going to put a 1, etc. It's got a B1. That puts a 1 here. It does not have a B comma 2, so that's why I have a 0 here. It lacks a C1 and it also lacks a C2, so I put zeros there. This relational matrix is a bit or binary matrix, and I put 1s corresponding to ordered pairs and zeros if they're not there. Another example might be R2, which is going to be a relation going from Y to Z, where it's the same Y I was talking about up here, the set 1, 2. And now I'm going to take it to another set, alpha, beta. Now I'm just going to make up a relation going from Y to Z. So I'm going to send 1 to alpha, why not? And 2 to alpha, and 2 to beta. That certainly is a relation going from Y to Z. What does its relational matrix look like? Well, if Y is ordered like this, 1 being the first element and 2 being the second, then that's the rows. And if Z is ordered like this, alpha first and beta second, then that corresponds to the columns. And again, if there's an ordered pair in my relation, I put a 1 in the appropriate spot. And if there's not, I put a 0. So you see here, 1 alpha is in my relation. It's right there. But 1 beta is not, hence that's got a 0. So that's the way you create relational matrices. Now, the way I've set things up, R1 goes from X to Y. And R2 goes from Y to Z. So guess what? That gives rise to a relation composition going from X and ending at Z. And if you'll recall, we call that relation composition R2 composed with R1. How do we figure out what R2 composed with R1 is? Well, one way to do it is an arrow diagram. So let's draw an arrow diagram. The first one is R1 going from X to Y. The second is R2 going from Y to Z, and I draw an arrow for any particular ordered pair. Here's R1 way up here. It's the ordered pairs A1, A2, and B1. So I've got A1, A2, and B1. How about R2? Well, R2 is 1 alpha, 2 alpha, 2 beta. So 1 alpha, that's this. 2 alpha, that's this. And 2 beta, that's this. Okay, and then what? My relation starting at X and going to Z is what we call R2 composed with R1. And by our arrow diagram, what is that equal to? The answer is what? A goes to 1, which goes to alpha. Thus, I have the ordered pair A alpha. A also goes to 2, which goes to alpha. Well, I already have A alpha. But then A goes to 2, which goes to beta. So that gives me A beta. And then what? B goes to 1, which goes to alpha, and that gives me B alpha. So as a review, this composition, R2 composed with R1, consists of the ordered pairs A alpha, B beta, or rather A alpha, A beta, and B alpha. All right, what does this have to do with relational matrices? And the answer is, whenever I have a relation going from X to Y, and I have another relation going from Y to Z, then of course I've got this relation composition that goes from X to Z, and as it turns out, its relational matrix is given by the product of the two relational matrices of the original relations. And I say it's almost given by the product. How does it differ? Well, the only difference is you take this product, which may have numbers other than 1, but you simply replace every non-zero number in this product with the number 1. All right. So previously we had the relation R1 and its relational matrix 1, 1, 1, 0, 0, 0. So I put A1. This is its relational matrix. A2 is the matrix 1, 0, 1, 1. And that's what I write right there. And so the product, A1, A2, is this matrix times this matrix. Now you'll notice that this is a 3 by 2 times a 2 by 2. So that's going to give me another 3 by 2. And the number of rows, which is 3, are going to correspond to the elements in X. And the number of columns are going to correspond to the elements of Z. And so remember, Z was alpha, beta, and X was ABC. And now if I multiply those matrices out, I claim I get the matrix 2, 1, 1, 0, and 0, 0. For example, the first element gives me a 1 times a 1, add a 1 times a 1. So that's 1 add 1, or 2. This element would be a 1 times a 0, add a 1 times a 1. So it's 1 times 0, add 1 times 1. That gives me 1, etc. The bottom line is that the product is this matrix 2, 1, 1, 0, 0, 0. Well, that certainly is not a relational matrix because I have the number 2 there. But if I replace that number 2, that non-zero element, with the number 1, then in fact I claim I do have a relational matrix, and it is the relational matrix for the relation composition 1, 2 composed with 0, 1. Composed with R1. Notice the difference. This is R2 composed with R1, but this is A1 times A2. And that is not a mistake. Okay, so if I read off this relational matrix, what do I get? The ordered pair is what? A alpha, A beta, and B alpha. And I claim that that is the composition R2 composed with R1. Is it? Well, let's go back and look at this composition that we computed way up here using the arrow diagram. And lo and behold, it is A alpha, A beta, and B alpha. Exactly what I got when I multiplied those two matrices and realized what that meant with respect to the relation composition. And that's all I'm going to say at this point.